I don't know who was still paying attention at the end of my not the last workshop, then the labeling workshop, but the intro to neural networks that I gave earlier. There was quite a few things. I guess this is kind of the clue here, but there was kind of a few things that were wrong. Well, first of all, like we were not getting quite a good accuracy. We are only getting 40%. I was wondering if anyone, in the audience has any clue as to why, maybe the choices I made were wrong, or like maybe some of the mistakes I made. Uh, was anything wrong with the architecture? Like, what do people think in general of the last, of using a feed-forward architecture on this? If there's any, there's no, just give me a few seconds. So if there's no answers, I'll just give the answer myself. So, well, I would say the main problem is we were losing this kind of two-dimensionality aspect, and by flattening the image into a one-dimensional column vector. And so by doing that, we were really losing a lot of the local connectivity of the image. So if you think, like, if you're looking at someone's face, well, the eyes are next to the nose and the mouth, but if I flatten this in a one-dimensional vector, I'm losing all of that information. So it's quite hard for a model to learn, to learn the proper representation of the image if you're already like, you're kind of destroying information when you're doing that. So really what you want to be doing is you want to be still working on the two-dimensional image. And so to improve this, very smart people, I guess, came up with the idea of convolutional neural networks. And the main idea behind this is to use convolutional layers, as you can, imagine. But the three main new concepts that come with convolutional layers are, first of all, the idea of sparse connectivity. So if you look at here, so at the bottom here of this graph, you see that this was kind of what I had earlier. So this is a fully connected layer. And you can see that every node is connected to every node in the output layer. And so that creates a lot of links. And you can guess that a lot of these are probably unnecessary. And if we were to use like some kind of regularization, some of these probably would go away for sure. So the idea is really to reduce this amount and really to have a sparse connectivity on just, small patches of an image maybe. And that's what we're doing in convolutional networks. And also to have parameters sharing. So the other problem here, if you look at this fully connected layer, is that every input gets all of its own weights. But what if if we're looking at a group picture and there's multiple faces and I'm building an algorithm to detect faces, does it make sense to learn new parameters for each face, or should I just learn one set of parameters and reuse it on each face? It would make sense to, you just learn one set. So the idea is also to, the new concept here is really to be able to share parameters, between representations. And I guess the third new concept is to have something that I guess we would call equivariant representation. So again, if you think of, maybe the, phase detection algorithm, it shouldn't matter if like I move someone in the image, left or right, it shouldn't really affect the algorithm at all. So the algorithm, as we say, should be equivariant to a translation at least. So, and this is something that we get, I guess for free for using convolutions. And really the idea, and when we are doing convolutions, is really we're working with this, we're going to be working with something called a filter. And a filter is pretty much what you think it is. So it's something that we will slide across the image from, from the top corner, from the top left corner to the bottom right corner. And what this filter will be doing is really, it will be just doing convolutions. And if you're not familiar with convolutions, you can just think of it as a simple, matrix multiplication, I guess, of or weighted combination of the weights of the filter, or the the parameters in the filter, and the pixels in the image. So really what we're doing is we're moving this filter across, and for each pixels, I'm calculating the sum of all the, the neighboring pixels, depending on the size of the filter. By the way, as you can again probably guess, the size of the filter, in this case, it's a 3x3. This is a hyperparameter, so you could choose that to be something else. And really what we're doing when we're sliding this filter is we're creating what we see at this end here, which is what we call the feature map. So a feature map is just a kind of a cool name for a, internal representation of what we are learning with our model. So I guess if we move on a little bit, the idea with convolutional neural networks is we're going to be stacking these filters in multiple layers to learn more and more advanced representations of the features in the image. So if we, for example, look at this car example, um, we're probably going to first be looking at, where are the edges, maybe where are the colors located, very low level features, as you can see in these very low level feature maps. And if we move on and we stack convolutional layers on top of convolutional layers, we're going to be building more and more complex features. And maybe hopefully at the end, we might be able to, detect, maybe wheels or windows or doors from the original image. And really all we have to do, to be able to do this is really just stacking layers. So I kind of briefly introduced the convolutional aspect with this moving filter. There's another aspect that you would want to be aware of in this max pooling that we call it. So really, when we're talking about pooling, we're doing pooling for two reasons. We first kind of want to keep the dimensionality down of our network, because depending on the way you do your convolutions, you could be actually increasing the dimensionality, which is not necessarily something you could be exponentially increasing it. So it's not necessarily something you want. So for this reason, and also to really impose sort of a bias towards the most salient features in the feature map, we're going to be doing this max pooling, which we slide, we are going to be sliding a bit like we were doing with the kernel, but across the feature maps. And we're going to be picking the maximum number, really. So we're pulling it into a smaller representation. I think I see there's a question. Yes, that's correct, Sarah. So really, this is all we're going to be doing really when we, and in between, I forgot to mention, we also will have activation functions, which really will be selecting which features from the feature map we want to keep and retain for future layers, and which one we kind of want to disregard depending on the input. So which, if we have a picture of a car, maybe there's wheels, but if we had a picture of a bird, there's no wheels, so we don't necessarily want to activate those. Depending on what's in the initial image. So really what we're going to be doing here is then, stacking these convolutional layers, activations, pooling, convolutions. And towards the end, depending on the tasks that you're going to be doing, if you're doing classification, very often the last layer is going to be a fully connected layer. So I guess as I was describing here, fully connected layer where we're connecting every feature, pooled feature map together with, an arbitrary number of nodes. And then to the final output. So if we're doing like multi-class classification like we are doing with CFAR, then we're still going to have 10 outputs here. So another thing I should mention is you probably were wondering, okay, so but we're sliding this filter across the image. What's going to happen at the edges, right? Because like if I put right now, like it's highlighting the 6, but what if I put it on the 3? Like what happens over here? And so this is why there's the concept of padding. So there's different ways to pad. You could pad with zeros. You could actually choose not to pad and say, oh, actually my filter, I'm only going to be doing it in a valid way. So I'm actually not going to go over the boundary. I'm just going to stay within the image. And in this case, you're actually going to end up with a feature map that is smaller than your original image in terms of, width and height. If you're doing actually a full if you're doing a full padding, you're actually going to end up with something that was bigger than the original image. And if you're doing a same padding, then it's just going to stay the same size. So it's really, it's kind of up to you when you're designing these models, which one you picked. Again, this is with, I find that with convolutional neural networks, there's a lot more hyperparameters than you typically have with fully connected networks. So just to briefly wrap up this kind of intro to CNN. So before we jump into the code, CNNs are really good for 3 things. So first of all, like really this locality aspect. So, neighboring pixels typically have the same color, or if they don't, then there's an edge. So there's this locality aspect that I really want to maintain and understand in images. there's also this stationarity aspect. So, in this case of the car, well, we have wheels, but a wheel in this part of the image shouldn't really be different from in a different section of the image. So we also want to be able to maintain that representation. That understanding. And the third one is really this compositionality aspect, where we're building features on top of features on top of features to really understand from a higher level what's going on, using lower level representations. So I'm gonna remain with CFAR 10, and so we're really gonna be working with the same data set as earlier, but I guess this time we will be using. Actually, we're gonna be using GPU. So if you're familiar with Colab, there's a way to use GPUs for free, which is the reason I'm using Colab, by the way, right now, because I didn't want to pay to access a GPU. So if you go in notebook settings, you have this option for hardware accelerator. I picked GPU because I wasn't sure if this version of PyTorch had the TPU support or not. I know TensorFlow does, but I'm actually not sure if PyTorch does. Yeah. So just to keep going here, yeah, so I'm going to be doing these all these imports. So as you saw earlier, we're importing Torch, Torch Vision, NumPy. All these things we introduced earlier, so that should be fine. So in this case, you'll see the GPU available should change to true, and it does. And now for the actual network itself. So I still picked a pretty simple architecture. To be honest, these days, like the convolutional neural network architectures are way more complicated than this. So I only have about 5 or 6 maybe convolutional layers, and a few max pooling layers. And again, we're sticking with ReLUs. ReLUs have proven to be quite a reliable way of doing activation functions without necessarily having a vanishing gradient. Because one of the problems when you're doing really deep learning is the problem of vanishing gradient. So when you're trying to propagate gradients from the end to the beginning, if your network is very, very large, that initial gradient is going to be smaller and smaller as you go across layers. So one way is to really mitigate that is to use the ReLU activation function, which is what we're doing here. So we're just going to be doing a simple convolutional layer here with 3 inputs. So because we're working with RGB pictures, we have 3 input layers, input channels, and we're going to be converting that into 32 outputs. And as I mentioned earlier, the padding. So we're going to be using a padding of 1 here and a kernel size of 3. So this is pretty straightforward. There's also the stride. So the stride is just the amount by which you move the filter each time. So we're going to be sticking with 1. It's pretty common. Yeah, what else? I'm going to be using max pooling with a 2x2 kernel. Yeah, so that's pretty much it. The layers, there's nothing more I think that I use other than convolutional. At the end, as I said, we're going to be flattening it into a fully connected layer, and we're going to be connecting that to a softmax to be able to do our multi-class classification essentially. So I'm going to be running that. I don't know if there's any questions. Do I know which GPUs I'm using? No, I'm not sure if anyone knows what's typically provided with Google Colab, but I don't think I'm not sure if anyone knows. Could I explain stride and padding again? Yes, for sure. So padding will just be the amount. So when you're at the edge here, you have to determine by how much you go over the image, because there's no image past the edge, right? So you have to determine by how much you go over. So that will be the amount of padding, and the amount of stride is just the amount by how much you move the kernel. So we're leaving the stride at 1, so really we're not skipping any pixels. We're just doing 1, 1, 1, 1. Yeah. So that's what we're doing here. So I'm going to be running this. And so this time around, I'm going to be loading the train and test set at the same time together. So again, using the torch data loader functionality. And so this time around, because I'm using GPU, I have to make sure that my both my model and my data are moved to GPU on the GPU memory. And so the way I'm going to be doing this is simply by calling CUDA on both the models, and you'll see later when I do it for the data. So once I instantiate the model, I'll just move it to CUDA, to GPU using CUDA. And then I'm going to be using the same loss function as earlier. So I'm going to be using the cross entropy loss. And again, I'm going to be using the same optimizer, which is Atom. Nothing really new here. And then I have these little functions defined just to be able to track. Well, I was using the accuracy earlier, so I explained that. We're really like counting how many predictions were the same as the labels they were supposed to be. Yeah, so we're going to be using the same accuracy function. Now for the validation, so I'm going to be doing two things to be able to measure the. So what I want to know this time around is what is going to be you can see here because I already ran it. What is going to be my training loss, my validation loss, and my accuracy after each epoch. So to do this, I've defined like these little helper functions. So really the main idea here is really to go over each batch in the validation loader. So, but if you did not understand earlier, when you create this data loader, you can specify it a batch size. In this case, I specified 10, but you can really specify what you want. And it's very common to use, actually, usually people use powers of 2, but in like 32. But in this case, I'm just going to be using 10. Sorry, I see there's a question. Google says, thanks, Antonin. Says it's a test like K80. Pretty good. Yes. Sorry, where was that? Yeah, so you can when you use this data loader, it automatically you give it the batch size, and once you iterate over it, because this is a Python iterator, it will give you it won't give you like one data point, it'll give you like a batch of 10 data points. Well, because I specified 10 here. So that's what you see here in this batch here is going to be actually 10 elements. So yeah, so let's go into this validation step. So really what I'm doing in this validation step here is really all I'm doing is I'm getting the images and the labels from the batch. So the data loader actually, when it provides us a batch, it provides us a tuple. So it's really just, I guess you could think of tuples are kind of fundamentals in Python. So if you're new to Python, you may be thinking like, what is a tuple? But it's really just I guess an n-dimensional list. So in this case, we have images and labels as part of the batch. So as I said, I also need to be moving because our model is on the GPU, I also have to move these images to the GPU. So I just have to call CUDA on them before I pass them to the model. Otherwise, it would complain. Yep. And same for the labels. I also have to put them on CUDA. And again, here I'm going to be using the cross entropy loss. This time I'm using actually the F, which is the functional API for Torch. And the simple reason being that like I don't actually want this to be like part of my computation graph or anything. I just want to know like what is the actual loss. So this is why I'm using this F here dot cross entropy. And then I'm going to be calling the same accuracy function I was calling earlier. Yep. And then I'm going to be logging this. Actually, I'm going to be returning this. So what I'm going to end up with here is actually an array of validation losses and accuracies. And so now the next thing I need to do is actually I don't want an array. I just want a singular value, right? So I'm just going to be computing the mean. So to do this, because we're working with tensors, I'm going to be using the, the mean as supplied by PyTorch instead of the, NumPy mean or, other types of mean, because otherwise I'd have to, get the NumPy version of the tensor, as I think I'm going to be doing later. Yeah, so I'm just going to be sticking, I guess, in the PyTorch sort of ecosystem or API to be doing this calculation. And because batch losses is actually this variable is actually a Python list. PyTorch is not going to like it, so I need to make sure first that I convert it to a tensor. So what I'm doing is I'm just stacking. In this, I wish I could show you the data, but this is going to be a list of tensors of dimension 1. So I'm going to be stacking these tensors together and just calculating the mean. So that's going to be doing here. And then I'm just going to be accessing the element in the tensor itself. So I'm going to be calling item. Yeah, so that's actually what I'm doing here. So this is going to be called at the end of each epoch to do sort of a validation estimation. Yeah. So this is it. Yeah. So yeah, I guess the other thing I should mention is I kind of like what I was explaining for this F here, because I'm just doing a, evaluation here. I really don't want like anything in terms of the, computation graph to be modified, because I'm just getting a value because I want to evaluate what's going on. And the same thing here, I'm putting this model into evaluation mode to make sure that like no gradients has changed, no calculation is made. Yeah, so I'm doing these two things for that reason. Yes, and then finally, I'm going through, I'm going to be building this training loop. So in this case, I'm going to be doing, I guess I picked 10 epochs here, but I guess it could be more. Let me just make sure I can run everything. I guess it's taking long because it's putting it on the CUDA. Yes, this ran. I'm going to run this. Yes. Okay. So I'm just going to be keeping track of the history after each epoch. So I'm going to initialize an empty history array, and then I'm going to be appending like the result of this evaluation that I just explained. And I'm also going to be calculating what the training loss was. So I'm going to be, let me just explain maybe this. So by doing this enumerate here, enumerate train loader, I'm getting a batch size 10, as I explained, because that's what I gave as a parameter to the batch size. Yeah, so I'm getting a batch of 10 elements. I don't know how big the data set is, I guess, but if it was a 100, there was 100 of them, and then it would run through this loop 10 times. So I'm going to be getting the loss at the end of each batch, and I should be saving it. Yeah, so for each batch, I'm going to be getting a loss, which I'll be appending to this array here. And I'll because I only want the training loss for an entire epoch. Again, I'm going to have to do a torch.stack the train losses, because it's a Python list, and then do the mean of it. Because I'm not interested in the training loss in the epoch itself. I only want to know what happened at the end of each epoch. So that's what I'm going to be again storing here. So yeah, so again, we have to do this optimizer.zeroGrad, because again, we don't want to be accumulating gradients. So we want to make sure that at the beginning of our batch, the gradients on each parameter is of 0. And then we have to move as I said earlier, we have to move our inputs on the GPU. So we're going to be calling inputs a CUDA, passing it to the model, and getting our inputs. Because both of these things were already on the GPU, both the model and the inputs, the outputs themselves are already on the GPU, so we don't need to worry about that anymore. And then we're going to be calculating the loss based on that. So again, we have to move, because this output is on GPU, we have to move the targets as well on GPU. No big deal there. Yeah, and so at this point, we've defined our loss function. We've defined our model. So all of our computation graph is fully defined, so we can call, loss.backward, and PyTorch will take care of calculating the chain rule and doing all the proper block propagation and leaving the gradient in each variable. And then we're going to be calling optimizer.step. So this optimizer, again, because we're using Atom, it will, by itself adapt the learning rate depending on where we are in the optimization. I should probably have run this before. Sorry about this. So I'm going to be running the training loop, and you're going to see. It's not going to be that fast, but trust me, this is going to be way faster than if I was running this without using the GPU support. Yeah, so it's still doing it's still in the first epoch. So I guess it's going to take longer than I expected. In the meantime, I'm not sure if there's questions, because I guess we're nearing the end of this this workshop. So we can already see that, I don't know if I'm gonna have time to wait until the end of all epochs, but our accuracy is already better than we were at for the previous model, and we've only done one epoch. So we can already see that our model seems already to be quite better adapted to our situation than the previous model was. Yeah. So I guess that kind of concludes it. I'm not sure if I went too fast over the details. I'm not sure if there's questions remaining. I mean, we can wait for this model to train more, but I think, I mean, you can see that the accuracy is only getting better, and towards the end, I was getting, I think, over like 75% accuracy if in only 10 epochs. Yeah, I don't know if there's questions.